All right. So now that we've talked about the electric force, we're going to go on to something a bit less familiar, which is this idea of a field. So a field is just broadly defined as a vector or scalar representation of some quantity that's defined everywhere in space. So what does that mean? Well, we can think about this in terms of acceleration due to gravity, because that's actually not just an acceleration, but it's also a gravitational field. Because if we look at sort of Earth's surface, we can define the gravitational field, G, at every point in space as just pointing directly downwards. And we might say that G has a value of 10 newtons per kilogram. So this means no matter where you place an object, it's going to feel a gravitational force directed downwards of 10 newtons for every kilogram of mass it has. So this is what a field does. It just allows you to quickly find the force acting on an object at any point in space. Now, this is not a really interesting field because near the surface of the Earth it's constant, but the fields we'll look at in here are going to be changing at different points. So we might have seen different examples of a changing gravitational field when looking at gravity inside a planet or far from the surface. So despite the fact that force is definitely familiar, fields are more fundamental because a force is just between two specific objects, whereas a field exists regardless of other objects. So if we're looking at the force on multiple things, it might be helpful just to calculate the field once and calculate forces as we need. And we'll also use for evidence that we'll see that you can actually store energy in a field where there's this circuit component known as a capacitor that stores energy in electric fields, and there's a circuit component known as inductors that store energy in magnetic fields. So these fields are actually very real and they store energy. They're not just a mathematical problem solving tip. So, one of my favorite examples of a field might be thinking about a wind map, because this definitely counts as a field, because at every point in space, I have defined my vectors that are indicating the direction of wind at that point. So, first of all, how would you determine the direction of the wind field at a given point? So, if I want to know what the direction of wind is outside my house, what could I do? Well, of course, there's the obvious answer, just stand outside and feel it, but how can we do something a bit more empirical? Well, every time I ask this, someone always finds like the answer I'm fishing for, which says like pick up a small object like a leaf or like a clump of grass and release it into the wind and see the way it flies. And this is a good idea of what a field is because we're actually going to define the electric field as this is the direction of push a small tiny positive charge would feel. Just like if you drop your tiny blade of grass in the wind, it will fly in the direction of the wind field. Or you could use a weather vane, which is apparently one word, that points in the direction. So you could also just consider using a device that's a sort of field indicator at that point. And why we might use the field approach in the news, so might be saying like if they said just for the field, the wind speed is 10 miles per hour south in Ann Arbor versus force, telling us how a 60 kilogram person would feel the wind force. Well, clearly, if you're not a 60 kilogram person, knowing the force on a 60 kilogram person isn't particularly helpful or efficient. So that's why we talk about this idea of field, because the wind speed being 10 miles per hour south is a lot more useful information than knowing about the force on one specific person. So force is specific to one object interacting with the field, whereas field is more general and applies to sort of a broader audience. So using this, let's think of these ideas when we define the electric field. So the electric field gives the direction of force on a positive charge. So these are just some facts that come from the definition. Positive charges go with the field in terms of acceleration. Negative charges accelerate opposite the field. So if I place a positive charge at a point, it will feel a force along the field and accelerate that way. Of course, if it's already moving, it could be going opposite the field and slowing down, but just think of the field as the direction of force on a positive charge. So as a result, there's alternate ways of thinking about electric fields. I call this the source and sink approach. So we'll say that positive charges are sources of field lines because they push lines out. Because if the field is the direction of force on a positive charge, that means that positive charges will not want to be near other positive charges. So any positives are sources. Similarly, negatives are sinks because positives will get pushed towards the negatives. So we can use this to draw electric field lines for a distribution, and I think this explains it pretty well. So for example, if I just picked some arbitrary point right here, we can see that a positive charge would get pushed radially out this way, and that makes sense because a positive charge would definitely not get pulled towards the existing positive charge. So we can see we call this positive charge a source because field lines are spawning from this location, and the negative would be called a sink because field lines are getting absorbed into that location. So anyone who's in a calculus 3 environment might be able to connect this to the ideas of divergence and curl, which I think are very important ways of looking at this in terms of what is a sink and what is a source and how that relates to something called flux. So let's draw ourselves some basic field distributions. So first we got a single positive charge. So first, we'll do each of these a different way. So first we'll just use the definition of the electric field. So if I just consider any point above the positive charge, a positive charge would get pushed away. So I know that this could be an electric field line, because if I place a positive charge above an existing one, it's going to get repelled. And I could repeat this for any direction of my choosing, and the analysis would still hold. And I could even choose some diagonals, that would work too. Because no matter where I place my positive charge, it is going to accelerate away from this existing charge. And notice this is consistent with our second rule. I didn't bring up the source rule at all, but we definitely call a positive charge a source. Now we'll use the second rule for the negative charge. So alternatively, we could start just with the fact that a negative charge is a sink. So using the sources and sinks rule, negative charges are sinks. So this means that any field line is just going to point radially in to my negative charge. And we can compare this. We can compare this to the other definition of the electric field, the more primary definition of the direction of force and a positive charge. So if I place a positive charge, no matter where it is, it's going to get pushed directly towards the negative. So consistent with the sink rule. And now we'll conclude with something known as a dipole, which is two charges of opposite sign. So the first field line, that's the only one that's really easy to draw, would be this one. Because if I place a charge anywhere on the midpoint line between the two charges, it's going to get pushed away from the source charge to the sink charge. And now if we consider a point sort of above the positive charge, it is going to get pushed mostly away due to distance, but it will get somewhat pushed towards that negative charge. So actually we end up getting this sort of distribution for a dipole field, where the lines curve a bit. You won't be expected to sort of totally replicate these field lines blindly. Like, there's never a field line accuracy drawing test, because we can see how bad even I am at drawing these. But we see that it's consistent with sources and sinks. So I could even draw like some even bigger radius ones if we wanted to, but again, that would probably be a bit excessive. The last distribution to really know is a really special case, and this is where we get an assumption in E&M that sort of annoys some people. This is known as the no edge effects rule. So if you think about it, if we take two plates of opposite charge, and it should be noted this is a 2 or 3D effect here. So we actually have these two plates. We're just looking at sort of a side view of them. We know that if one of the plates is positive and the other is negative, we know that we're going to get some nice field lines that are just going to go from the source to the sink. So what we think is going to happen is that we think that we're going to get a nice uniform field that points directly from the positive plate to the negative plate all throughout the plates of the capacitor. And that's a pretty good approximation for most points. So we will call this device of two parallel plates, we call this a capacitor. And we will assume the field is constant and it's directly pointing between the two plates like this. Now, when we start to have an issue, which we'll explore in this next part, is if we investigate sort of near the boundary, which we won't actually investigate in problems in this class, but it's important to know conceptually. So first of all, in this course, we're going to make the approximation that the electric field within the place of a capacitor is uniform. So using our field diagram, justify this approximation. Well, away from the edges of the plates, the lines point directly to the right, source and sink rule, right? If I place a positive charge, it's going to go away from the positive plate and towards the negative plate. Now, instead, what if we looked at the sort of boundary? So we're ignoring, this is actually in the list of assumptions of the class in this sort of exam booklet. It says edge effects are negligible. So maybe we'll draw the edge effect lines in a different color. So if I'm somehow like near the edge of this plate, we know these field lines are actually going to curve a bit because they're not totally going to get wrapped up inside the capacitor like it did before, because you're sort of breaking that symmetry. So if we're outside the capacitor plates, or at least near it, it starts to curve off and make this dipole electric field. So it's important to know that this is the real capacitor field where it starts to kind of look like a dipole, but all of our useful math in the course will be happening in this region where we're much, much closer to the center of the plates. So we assume the plates are either really, really large or we're not going near the boundary so that we can do some really nice math with uniform E fields. So near the edges, the field lines curve, making it look sort of like that dipole E field from earlier. So now we can use the fact that the E field gives the direction of force on a positive charge to do this sort of analysis. So suppose that we have a physical dipole that's connected by some sort of material or atomic bond. So we're actually just sort of modeling some sort of atom here or molecule that are bound together by something. And first we want to draw the direction of the net electric force on the charge due to the E field. So we know for sure that positives feel a force along the E field. So U will feel a force along the E field this way. And then if positives are going to get pushed up by this E field, then negatives must get pushed down by this E field. And it's given that these charges have the same sign, or sorry, same magnitude but opposite sign. So we know that the electric field is going to push on these charges equally. So now we can do some analysis. Indicate the direction, if any, of the net electric force on the two-charge system. Well, there's none, because there is a upwards force on one end, but there's a downward force on the other. So we can conclude here that the net force is 0. But we could also look at the torque or rotation of this system. Because if we look at the rotation of this system about its center, if I think about this as a clock, the positive charge about its center right here, the positive charge would get pushed clockwise because that's going to rotate clockwise. Think about just a bar attached to the table. And the bottom charge is going to rotate also clockwise. So this actually doesn't cancel. So you're actually going to get a net rotation about the system's center of mass here. So you get this net torque. It's going to be clockwise. So even though there's no force on this dipole, it will still rotate. So be on the lookout for conceptual questions like that ask you if this system rotates, because it could. Even if the net force is 0, this is still going to rotate. And this isn't the only time that we'll look at rotation in this class. We'll also see that magnetic fields can cause rotation as well. But why was it during this analysis that we didn't look at the force between the charges at all? So why didn't we look at the fact that, yes, this charge is connected to this? Why didn't we look at this sort of internal force between the two for the net force on the system? Well, as we can see by the picture, these forces also just sort of cancel out. And it doesn't matter what was going on with these charges, these forces will always cancel out because it's a Newton's third law pair. It's just those equal opposite pair forces. So why does this, well, gotta move this, my picture. The force between the two charges is internal, so it can't be a net force, or you want to just think about it using Newton's third law. So these forces are going to be equal and opposite, so they're not going to contribute in any meaningful way. So no harm in ignoring that force. So now we can quantify the electric field, because if we define the electric field as the direction of force on a tiny test charge, this means that we can use it as a force per unit charge. And what that allows us to do is convert from field to force. So if you know the field at a location, you can easily calculate the force by multiplying the field by the quantity it acts on. So we actually have this sort of general expression that says the force is going to be equal to some sort of quantity times the field. And let's capitalize this. Because that's what fields do. They allow you to figure out the force on some sort of representative quantity. And we'll connect this to the familiar example of gravitational force is mg. Because gravitational field is a field that acts on mass, and that exerts a force. So notice that Fe equals QE is analogous to this mg situation. And that's not a coincidence at all. It's really just what a field is. We just are so used to talking about it in terms of other terms. So first, let's verify that the units of this quantity called electric field are going to have units of newtons per coulomb. So not a very hard task here, because by definition, by definition, the electric field is the force per unit charge acting on a particle. So force is, of course, measured in newtons, and Q is measured in coulombs. So we get our unit of newtons per coulomb as expected. And that gives us a really nice way of interpreting the magnitude of the electric field. So just like you might write G, just like you might write the quantity G as 10 newtons per kilogram to tell you how many newtons are exerted on each kilogram of mass, the electric field tells you how much force is exerted on each coulomb of charge. So here's an example of some balanced forces. An electron of mass m is placed between the plates of a capacitor. The capacitor is charged, and the electron remains floating at rest here. So first of all, we know that if the electron is just floating here, we know it, of course, is going to have a gravitational force mg downwards because it has mass, and it must be experiencing an electric force upwards. So, if it's experiencing an electric force upwards, there's sort of two approaches we could do with this. So the easier one, I think, is just looking at attraction. Because if the electric force is up, it means it's being repelled by something below it and or attracted to something above it. So the only thing that's consistent with that would be, by definition, a capacitor is two opposite charged plates. So we know the top plate is positive. The other way of doing it would be understanding that the electric field exerts a force opposite its direction on a negative charge, or a negative charge experiences a force opposite the electric field. So if I'm experiencing a force up and I'm an electron, there must be an electric field directed down in this region. And how could there be an electric field directed down? Well, source and sink rule says the top is positive, bottom is negative. So it's all consistent. Oh, here's our free body diagram again. Probably should have given us a grid here. What are the forces on the electron? Well, of course, there's a gravitational force down, and there's an electric force up, and these are equal. So suppose the electric field between the plates is E, derive an expression for the mass to charge ratio of the electron. So this is not that dissimilar to something known as the Millikan oil drop experiment. Turns out this quantity mass to charge ratio is quite important. So by force balancing, we can set the up forces equal to the downward forces. This is just a Newton's first law situation. So my electric force acts up, my gravitational force acts down, and we cannot use like KQQ over R squared because we're not given a point charge here. So we have to use the more general fact that electric force from anything, so here's another benefit of electric fields, is that it works for even non-point charges, is electric field is given by QE. And again, I gave this right next to mg so we could compare just how similar these formulas are. And what we want is the mass to charge ratio of the electron. So you might call this little q, you might call this like a lowercase e if you wanted to, but we want mass to charge ratio. So that's mass to charge. So I might say that the E is equal to m divided by q, which is what I want, times g. So therefore, my mass to charge ratio, mass to charge, is equal to the electric field over the gravitational field. So we get this interesting fact that the ratio of the fields is sort of the inverse of the ratio of the quantities the fields act on, which sort of makes sense. Because if you have a bigger mass, you would need a bigger gravitational field to sort of get that same force. All right. Now we can do the electric field from a point charge. So we already talked about what the electric force is between 2 point charges, and this looks very, very similar to Coulomb's law. There's just one Q, which makes sense because forces are between two objects, but fields, sources and sinks, they can just exist by themselves. So let's just verify this rule real quick. Verify the expression for electric field using the definition. So by definition, the E field is the force per unit charge. And Coulomb's law states the force between two charges is kqq over r squared r hat. So if I'm just dividing out a test charge from that, this tells me that the electric field from a point charge is just Coulomb's law with one of the charges removed. So just like we said before, no signs here. No signs. Because this is a vector quantity. So maybe we should just write this again. No signs. Include a direction on the end of your answer. Vectors are not plus or minus. Vectors have direction. So is this consistent with what we said about field lines? Well, absolutely. Because r hat is a vector that means out. So if I have a positive r hat, which I'd get from a positive charge, that would be a source. If I get a negative r hat, that would be a sink. So positive charges, field lines point away from the charge, negative charges, they point in. So this is literally the sources and sinks rule. Great. So here's a point charge. We have just drawn some circles of radius r, 2r, and 3r around it. First, let's draw some field lines. So, no need to overcomplicate anything here. Positive charges, you are a source, so I'll just do my best job at making some nice equally spaced source lines here. Definitely way better than when I've freehanded it in the past. Again, notice this is definitely consistent with our just main definition of electric field, because anywhere I place a positive charge, it's going to get pushed radially out. So we see this is a source of field lines. Suppose the field strength at the first circle is E. We want to figure out the field strength at the other two circles. So by definition, the magnitude of the E field is just kq over r squared. So this is really just testing our knowledge of functional dependence. So if I am going from r to 2r, I am just doubling this denominator. So I have to remember that I am just squaring the distance, so that term on the denominator. So my electric field would only be a fourth of what it originally was. We can probably guess what's going to happen if I, instead of going one circle out further, I go out two circles out further, so I get to 3r. So instead of doubling the distance between the source and the point of interest, I triple it. I triple r, but the thing I tripled gets squared in that denominator, so I get a ninth of the E field. Now we'll do a quantitative example. So we have a 16 microcoulomb charge, and again, we know what micro means. Micro is 10 to the minus 6. We place it at x equals 2, and just based on spacing, we can see that these are spaced by 1 meter. So if these are spaced by 1 meter each, first we're going to just draw the direction of the E field at each point. So maybe I'll go try to be at least somewhat quantitatively accurate here. So we know that my field, you are a source. So this is a source of field lines. So I know lines are going to radiate out. And as I get further away, this field is going to decay. If I was being really accurate, you can barely even see it at those far points. So now let's do some calculating. We do want these in unit vector notation. Electric field at x equals 0. Well, E is kq squared. No, not just 1q. E is kq over r squared in terms of magnitude. So k is 9 times 10 to the 9th. Q is 16 microcoulombs, so 16 times 10 to the minus 6. And the distance, well, I want the electric field at 0. 0 is 2 ticks away from the point charge, so that's 2 squared on the bottom. And now we tack on our direction, because the electric field is a vector. So I can see based on my picture, this points left at x equals 0. So I'm going to tack on a negative I hat to indicate left in this case. So this would mean that my electric field, typing all that in, is 36,000 newtons per coulomb in the negative I hat direction. Now the electric field at x equals 4. Well, by symmetry, x equals 4 is also 2 ticks away, but we see it just points to the right now. So we don't need to calculate it. We can see it's just going to be the same thing, just in the right. So it gets a plus I hat vector attached. Now we want force. The force acting on a 100 nanocoulomb charge placed at x equals 0. Well, luckily we calculated the field already. You can use Coulomb's law for this if you wanted to. With the charge that's already there and the one I just added, you could do that. But this is about electric field and just showing you that it's pretty convenient because we have this expression that just F is equal to Q times E, as long as we're doing everything as vectors. So in this case, our Q is 100 nanocoulombs, so nano is 10 to the minus 9th. And the electric field at x equals 0, we said is negative 36,000 newtons per coulomb I hat. And another reason we use field is you can put the vectors right in this thing and it works out nicely. All right, so we know it's going to be negative 3.6 times 10 to the minus 3 newtons I hat. And maybe I'll like make this I hat a bit more pronounced, that it's something different than the unit. And let's make sense of this. We said this is a force to the left. Does this make sense? Well, if I place a positive charge at x equals 0, yeah, absolutely, it's going to get pushed to the left. 1, because the field pushes it to the left, because that's what we said. And also, I know it's going to get repelled by that positive charge. All right, next, let's do an electron placed at x equals 4. So once again, we'll use F equals QE. And we actually do know Q. This is in our reference sheet. Q from a positive, from an elementary charge, proton or electron, is 1.6 times 10 to the minus 19th coulombs, but an electron is negative. So I will attach that negative because this handles that reversing the field direction idea. And at x equals 4, we said the field was just positive 36,000 newtons per coulomb I hat. So we can evaluate this, and we get, once again, an answer that's negative in a negative I hat direction, 5.76 times 10 to the minus 15th newtons in the I hat direction. So this is saying that if I place an electron at x equals 4, that is getting pulled to the left. Does that make sense? Let's see. Well, the electric field points to the right at that point. But that's not an issue, because that's telling you the direction a positive charge would feel a force. So since it's a negative charge, absolutely makes sense. It's getting attracted, moving against the electric field. So now let's make a qualitative graph of the horizontal component of the electric field on this interval. So we see that before I reach the point charge, which is going to be an infinite spike, because my distance would be 0, so I'd be dividing by 0, which is going to be a vertical asymptote at x equals 2. I'm going to get an electric field that eventually decays towards 0 in the negative direction, and then as soon as I pass x equals 2, it's going to decay towards 0, but be a positive. So we would get something we get something that sort of looks like this, which is a very odd sort of graph to get in a physics class, something with a vertical asymptote. But that is what we get. Because again, we're saying that this is representing the leftward push, and we know that as you get farther and farther away from this point charge, this infinite spike of field, we are going to decrease that field strength because the force generated on a charge there would not be as large if you're far away. Is this consistent with the direction of field vectors drawn in part A? Well, given that I just graphed this using the direction of field vectors, I sure hope so. It's consistent because it points to the left when x is less than 2, so that's below the axis, and then it's above the axis when x is greater than 2. Exactly what we drew. All right, now we can connect this to force and kinematics. So a positive point charge with mass little m, charge q, and velocity VO enters a region of uniform electric field. We want to find the final speed of the particle with different E-field orientations. So first, we're going to do sort of the base case of this, where I have a positive charge that moves at velocity v0. And for laziness reasons, I'm just going to copy-paste this a few times. Our first case is the E-field points with the charge's initial velocity. The second case will be the charge, the E-field points against the initial velocity. And the third case will be the E-field points perpendicular to the initial velocity. And we are interested in finding the final speed. So the reason the E-field helps, in each case it's going to spend time t in this E-field. The reason the E-field helps is because we know that for all of these problems, we can use the fact that the electric force is going to be QE. And also, we can use Newton's second law that says acceleration is going to be F over m, which is going to be QE over m. So, in each of these cases, the acceleration is going to be QE over m in some direction. So, first, in this case, we know that the acceleration is going to be, we're going to call this plus QE over m in the same direction of the object's velocity. Because if a positive charge travels with the E-field, it's going to speed up. Or it's going to feel a force with the E-field, so it's just going to stack on to make it larger. So in each case, this allows us to we'll use this kinematics, that Vf equals V0 plus AT. So our final velocity is just V0 plus QE over m times t. And notice this makes sense for this first problem because my final speed will be in the same direction, it's just larger. Second case, you can probably guess what's going to happen now. Because if I go against the E-field, this positive charge will feel force opposite the way its velocity is going. So we can just denote that by a negative acceleration. So the only change is just going to be the sign splitting my initial velocity and the delta. So now, what is this third case going to be? Because we have pure addition originally, because again, in this first case, we're going to end with something like this. In our second case, we're going to end with something like this. Or in an even more extreme case, it could be so large that it speeds up in the other direction. And then, what could case 3 be? Well, it's not against the field, and it's currently not moving against the field in any way. So it's going to get pushed with the field and accelerate that way. So it is actually going to feel an acceleration in the y direction of QE over m. So this will actually add velocity. It's just going to add velocity perpendicularly to the original. So my final velocity in the y direction is going to be this sort of extra velocity I gain from moving perpendicular to the field. So this isn't the final speed. This is just the velocity it gained in the y direction. So we'll draw this out to better visualize. So if this is my velocity v0, and this is my extra velocity I gained, QE over mt, going perpendicular, then my final velocity is just going to be slanted. And how do I find the speed? Well, that's just the Pythagorean length of this. So in this case, my VF would actually be a Pythagorean theorem result. So rather tricky, but I thought this was an insightful example because we can see exactly what the field is doing in each of these cases. So again, in the first case, it's just pure addition because you go with the field. In the second case, it's pure subtraction because you go against the field. And in the third case, it is still addition, but it's in a different dimension. So the addition occurs, but it has to be a Pythagorean theorem situation. So we can get very different things. Realistically, I would expect this more as a ranking test, where could you correctly rank that the speed would be the fastest in A, the slowest in B, and intermediate in C. That would be more of what I'd ask. So all of that was just one charge. So of course we can add multiple charges and deal with our problems that way. So with superposition, the effects are the same as before, where you just figure out everything from each charge separately, then add the results. So we're going to rank the E field along this line. All of these tick marks are spaced by D. So first I drew myself my nice little blue charge here. So the blue charge, you are a sink. So there's going to be a large field generated towards you from A. There's going to be a large field generated towards you from B. But then C is farther away, so it's going to be a tiny field generated at C. Still a sink, though. All right, what about my green charge? Well, we can see for my green charge, you're a source. So it's going to make a large source at C. It's going to make a large source at B, and it's going to make a small source at A. So now we can just totally compare these fields without doing any math, because we can see the fields add at B, because the arrows add, and they subtract at A and C. But due to symmetry, because it's that same distance, we see that C and A are going to be equal. It's just which arrow is longer originally. Is it the blue or the green? But it is the same sort of cancellation happening. Not total cancellation, but it's just partial. So we see that EA and EC tie because they are not as long as B. So this really just turns out to be an addition/subtraction situation. So the electric field is, of course, the vector sum. The fields add at B and subtract at A/C. And by symmetry, A and C are the same because it's one tick from one charge, but it's 3 ticks from the other. So now we can derive expressions for each of these field magnitudes. So it's going to be the same idea for all of these problems, where I just want to check how I named it here. Blue is negative. Okay. So my E at each point is just going to be the E from the negative charge plus the E field from the positive charge. And I do have to take vector things into account for this because the direction does matter. I'll set this up here. So we can see that for my EA, well, A is 1 tick away from the minus Q. So we get KQ over D squared as the contribution. And then since there's a sink, we see this points right. So this would be a plus I hat. And then my E from the negative, my E from the positive Q, we get a KQ, but it's not 1 tick away. It's 1, 2, 3 ticks away. So my denominator is actually 3D all squared. And this is a leftward field, so this is negative I hat. So if we do some combining here, we see that we'd get KQ squared over D squared I hat minus 1/9 KQ squared over D squared I hat. Just factoring out that negative to show that we have a subtraction of fields here. So I have a 1 minus a ninth, so that makes 8 ninths kq squared over d squared to the right. And we just wanted the magnitude, so we'll just box that part in. All right, we can see what's going to happen at B. So at B, both fields are going to be directed to the left. So we have kq over d squared negative I hat plus also kq over d squared negative I hat. Because both point charges q generate a leftward field, and they're exactly one tick away. So this just becomes 1 plus 1 equals 2. Oh, it's not a q squared. I don't know what I'm doing up here. It just makes a 2kq over d squared negative I hat. And of course, we don't want the direction. We just want the magnitude. And we don't need to see me do C. You can see by symmetry. The only thing that's going to happen is these blue and green terms exactly swap places. So EC is going to be we're just going to do the classic cop-out answer. By symmetry, EC equals EA, which is equal to 8 ninths KQ over D squared hat. And we just want this term. So for the consistency check, EA, 8 ninths in front. EB, 2 in front. EC, 8 ninths in front. So we can see that this is consistent. Because we get 8 ninths KQ over D squared, which is the same as 8 ninths KQ over D squared, which is less than 2 times KQ over D squared. So we see that EA was equal to EC, which was less than EB. As expected. Now we have one of my favorite E-field problems. It's the sort of zero field location. So we have these two positive charges, and we're interested in the location between them where there's no field. So first, let's justify this exists. So if I'm really close to this plus Q, I'm going to get pushed to the right due to the source rule. But the 3Q is also a source. So if I get really close to the 3Q, this should point to the left. And I can't just instantly go from right to left, so there must be some crossing point. So that actually allows us to make this claim that there is going to be a zero location. So how I'd like to do this first is let's just guess that it's the midpoint. Let's say that we thought the midpoint is where there's zero field. Well, there is a source from the Q, but there's also a source from the plus 3Q. And since I'm at the midpoint and my distances are the same, the 3Q is dominating at the center. It's actually generating a field 3 times larger. So I know it can't possibly be the midpoint. So if I'm trying to make the blue arrow stronger and the green arrow shorter, I gotta shift this entire system this way until I get the forces to balance. So I actually know it's going to be over here somewhere. Because I have to get far enough from the green to shrink it enough, and I need to get close enough to the blue to make it grow so that these fields exactly balance. So it's going to be closer to the plus Q, the smaller charge. So any argument like that would totally work. Let's see what me from the past said. Since both charges are positive, the fields produced by each charge will be opposite directions. The 3Q charge is larger, so you need to get farther away from it to generate the same field with A plus Q. So the balancing point is closer to the left. So let's drive an expression. Let's solve this, and hopefully we are correct. All right, so what we want is we want the fields to be equal in magnitude. So we want the electric field from the Q charge to be equal to the electric field magnitude from the 3Q charge. Our expression, so now let's figure out how to set this up. So U were plus Q, and you were plus 3q. So we do know that our point is going to exist somewhere over here. And we said that this point is called x0. So you are x0. And then that must mean that the remaining distance is the entire line width d minus whatever I used up. And we can see by segment addition, these two lines add up to d, so you know it works. So now we can just set it up because we know that kq over x0 squared equals k times 3q divided by d minus x0 quantity squared. So now we can go ahead and cancel some things. So the k's cancel, the q's cancel, so I just get 1 over x0 squared equals 3 over d minus x0 quantity squared. So now I might push all of the squared terms to one side. So I might write d minus x0 over x0 all squared is equal to 3. So this means d minus x0 over x0 equals plus or minus square root 3. So d minus x0 equals plus or minus root 3 times x0. So d is equal to x0 plus or minus root 3 x0. So d is equal to x0 times the quantity 1 plus or minus square root 3. So so x0 would therefore be equal to 1 divided by 1 plus square root 3 times d. And I disregarded the minus term because if you check, if I plug that negative in, I don't get an answer that's within the 0 to d range. I'd get a negative answer. So that's a lot of work. And there is actually a clever solution to this problem that doesn't involve nearly as many steps that I think is useful to go over. So there is another way of doing this because this is a lot of algebra. So there goes all our work. But that's okay, because if we instead look at this again, where you are r plus q, you are r plus 3q, and this magic distance is x0. So here's the key insight. We know that E is proportional to q divided by r squared. So this means for same electric field, you would need q over r squared to be the same. So we would need the same q divided by r squared. So in this case, our charge is tripled. So to generate the same electric field with a tripled charge, I must be tripling my denominator. So I must be root 3 times further away. So I must be root 3 times further away so that when I square that distance, it works out to 3 on the denominator, so the 3 and the 3 work out. So what that means is that tells us that actually this distance isn't just arbitrary, it's exactly root 3 times farther away than my x0 point. So knowing that I need to end up tripling my denominator, so I have to go up by root 3, that's a pretty tricky insight. But if you have that insight, we can now really quickly say that those two segments together add to d. So that means that x0 times 1 plus root 3 equal to d. Same answer. This is definitely a more elegant approach, but it's not the one you're going to see as much because it requires a lot of like really good proportional reasoning skills. I think it's a great problem, but again, tricky. Describe how x0 will change under each of the modifications. So suppose we change both signs of the charges. Well, if we change the sign of both charges, all that's going to do is change the direction of the green and blue arrows. So those will both flip. so nothing. But if you change one sign, only, that would only flip one arrow around, so you'd get arrows that would add instead of subtract. So you actually wouldn't get a solution. So a key aspect of this problem working is the charges being of the same sign. All right, here's a 2D superposition example. Two equal and opposite point charges have magnitude q, and they're placed at opposite corners of this square. So first, let's find an expression for the electric field strength at the top right corner of the square. So once again, let's color our charges. So you are a source. You're going to generate a field. You're a sink. You're going to generate a field. And due to symmetry, we actually know that these two fields are going to have the same magnitude. And we just actually want that magnitude of the net electric field at the top right corner of the square. Well, we have a leftward field, or sorry, that is right. And we have a downward field. And both of these charges just have q and as their charge and their distance s away because it's just a single vertex. So they're both just 1 kq over s squared is their contribution to the field. But these fields are oriented perpendicular, so they don't just add. They don't just add or subtract like some of the ones we saw earlier. This is another Pythagorean situation. If you really know your special triangles and saw these were the same length, you could see this as a 45, 45, 90. But if not, we could see that the magnitude of the net electric field is just going to be kq over s squared times the Pythagorean theorem with both of these sides. So 1 squared plus 1 squared. So you just get your root 2 kq over s squared. All right, now we can derive an expression for the net field at the center of the square in unit vector notation. No. We're going to do the magnitude. We won't need to do that. I guess I wrote it. Why not? I can suck it up and do it. All right, center of the square. Plus q. You're a source. Minus q. You're a sink. Notice that these fields actually do directly add. Maybe if I could draw properly, you'd see that they both point towards that bottom right corner of the square. So you can see just by source and sink rules that this works out nicely. So actually, the magnitude of the net electric field is just twice the field from 1. So we know the magnitude of the net field is just 2 times the E field from 1 charge. So now we just have to figure out what the distance is, because it's to the center of this square. So we can draw ourselves a little picture down here that if this is S and this is S, the diag is length S square root 2. But we just want the distance to the center, so we want half of that. So that's half of S root 2 that goes on the bottom before being squared. So if we work that out, we end up getting 2 times kq over 2/4 s squared, because the root 2 becomes a 2 and the 2 becomes a 4. So that is a divide by 1/2. So this actually just becomes 4 kq over s squared is the magnitude. So we could stop there if we wanted the magnitude, but I wrote find the components, so let's do it. So we know that the E field, if we actually want to break it down, we can write this as E times cosine theta in the direction it acts plus E times sine theta in the direction that component acts. So our problem, we see that it goes down and to the right. So we'd get an I hat on the X term, and we'd get a negative J hat for the Y term. So this is a square, so we can work this out very nicely. So the 4kq over s squared factors out of everybody. and we'd get a cosine 45 degrees I hat minus a sine of 45 degrees j hat. And this is root 2 over 2 for both of these. So I could just factor out root 2 over 2 for both of these, and I'd get 2 square root 2 kq over s squared times the unit vector combination I hat minus j hat. So kind of ugly, but alas, I did not chicken out, and we actually did this. Alrighty. Last one. Got a long one today. Two particles of positive charge q are placed along the y-axis at plus or minus a, and we're going to be interested in the field along the x-axis. So we have another 2D problem. So whatever will we do if there's multiple charges? Well, of course, we'll draw each charge by itself and give ourselves some contributions from each using superposition. And man, I cannot draw diagonal arrows today. So there's our plus q, there's our other plus q, and we can see what's going to happen by symmetry now. Because we have an up and to the right field and a down and to the right field. So we see that vertically, we see this component gets canceled by this component. So we are going to have a net electric field that just adds directly to the right. So this is our net electric field. So the top charge generates a field down and to the right. The bottom charge generates a field up and to the right. So these vertical components cancel, making us have a net field to the right. And if we'd like to prove it with some tip to tail vector addition, this is E. This is also E. That makes our net electric field just entirely horizontal. So now let's find the magnitude of this field. So this is very similar to the triangle example because we don't want the full field from either charge. We just want the x components because that's actually what's adding here. So my net electric field is just going to be 2 times the x components of one charge, the field from one charge. So what this allows us to do is, well, let's actually draw ourselves out a little triangle here. Because we're given a distance x0 along the axis, or just x actually. So if I just draw one of my charges, I get this as my triangle. So this distance is x, this distance is a. And because we're going to need it, this distance between the charge and the field point that we're evaluating at is going to be square root x squared plus a squared. So now what that allows us to do is I know I'm interested in this angle theta right here because I want the horizontal component. So I want to extract the component that touches that angle. I'm going to use cosine. So this would actually just be 2 times the magnitude of the E field from one charge times cosine of this angle theta. So this means that my E field is going to be 2 times kq over the Pythagorean distance squared, so that eliminates the square roots. And then we have to deal with cosine theta. So cosine theta, we actually just use the SOHCAHTOA definition of cosine, where cosine is defined as adjacent, x, because it touches theta, divided by the hypotenuse. And then we get quite the answer to have to simplify here. Numerator isn't bad, it's 2kqx. And then for the denominator, I have x squared plus a squared to the 1 times x squared plus a squared under square root, which is a 1/2 power. So I have a 1 power times a 1/2 power. So by exponent rules, that's 1 plus a half, which makes that x squared plus a squared to the 3/2. So that is something that we've seen once now. This will come up a lot. If you ever see that 3/2 power show up, it's from this cosine or sine idea, where you end up tacking on an extra square root factor. And to conclude, we have this idea that if you go really, really far away from this and zoom out, it won't look like 2 charges. It'll just look like a single charge. So I always connect this to resolution. If you're driving and you see a car's headlights, if you're close to the car, you can see two headlights, but if you're really far away, they blur together. That's what this is saying. So let's see if we go really, really far away. So if our x is really, really big compared to a, this should just look like a clump of charge 2q. And we shouldn't really see that Pythagorean distance. It should just look like we're entirely horizontal. All right, let's see. So if we're really far away, that means that x, the distance along the x-axis, is much, much bigger than the charge separation. And what that allows us to do is this means that adding a small number to a really, really big number does practically nothing. So this term is still roughly just x squared. Because if x is 1,000,000 and a is 1, 1,000,000 squared plus 1 is basically 1,000,000 squared still. So this means that our net electric field is roughly 2kqx, divided by, we said that we can practically ignore that little a term if our x is really large. So I'm really just taking that x to the 3/2 power. And a 3/2 power applied to x squared results in x cubed, which results in 2kq divided by x squared, which is very promising. And then just a quick regrouping allows me to write this as k times 2q divided by x squared, which is the expected result because this looks like k times the net charge divided by x squared. So that is exactly what we wanted to find here. Yeah, a lot going on with electric fields. And that's just the algebra part. We still have some calculus to do also.